Hi there, I'm Glenn Morris from the Smart Energy Lab, and today I'm at Arvio Australia's new factory in Melbourne. Looking at their amazing containerized battery energy storage system. Now this is something that has grown over time. Started with Arvio building their very own Titan battery. So I'm here with Paul Wilson from Arvio Australia. G'day Paul.
Hey Glenn, how are you?
I'm good. Every time I come here, I'm just amazed at what you've done. It gets bigger and better, and it's very much Australian content.
It's a lot of Australian content in here. The cable, the inverters, the charge controllers, the batteries, the software, everything really, all the labour. Okay, so the client is actually, the name of the client is the Great Stupa. It's a funny name for those who've heard it for the first time, but I think Stupa means temple. And the Great Stupa is a large Buddhist temple in Bendigo. And this particular client had a problem where there was an existing two-phase SWER line coming in, with just 50 kVA of power available for the entire property. And they wanted to build apartments and homes and power more and more loads, and they couldn't do it with a SWER line. There was no three-phase power. And so we said, well, why don't we design a system to bring in the two-phase power and then convert it to DC, then produce a three-phase supply for you. And that'll give us the ability to add a lot more solar as well, because we're off the grid. So we designed a system where we brought in two inverters off the SWER line, produce a DC bus, and then we reform three-phase over here. And then we also have a backup generator for these three phases if we wanted to run completely off-grid.
Right, so the customer had two-phase, you're giving them three-phase and more capacity.
We're actually giving them five-phase power, which is phase A and phase B, which is the two SWER line phases. They're 180 degrees apart, and we're returning them to them as usable AC supplies. And then we're using those two inverters to charge a DC bus and a battery bank, our own battery bank here, which we'll show you in a moment. And then we're reforming three-phase on site. So we have 5 different phases on site, 2 single phases which they can use, and then a pure three-phase solution.
So we're standing in front of the three-phase system here, which consists of what, 3 20 kilowatt SP Pros?
Yeah, these are 20 kilowatts each. That's phase 1, 2 and 3. And then that's phase A and B over here.
And down this end we've got the SWER system, which is...
Yeah, so we have SWER 1 battery inverter and SWER 2. And they bring in the AC from the grid and then charge the battery bank through this DC distribution system. And so the energy storage system can fill up. In this case we've got 125 kilowatt hours of storage, and the ability to charge this battery really as fast as we want. It can charge it in around about 20 minutes based on the size of the fuses, and that lets us have an enormous amount of peak power. So we can be charging from the grid, charging from solar, and charging from the generator all at the same time if we want to, or any of those feeds. And then we can be producing 2 phases or 3 phases or both all at one time.
So tell me a bit about the Titan battery. How did they come to be?
Well, we were using another battery technology from overseas, and it was hard to get support being so far away. So we decided we'd spend the time learning from what we'd learned from that manufacturer and improving it. And so we developed this battery range here called the Arvio Titan. And so basically in each module here is 6.2 kilowatt hours of storage, and with a C rating of 6C. So it can charge up in 12 minutes.
6C?
Yeah.
You can charge it 6 times the C rating?
Continuously.
Wow.
But you can charge faster if you want. You can charge it 10C, but just for shorter periods of time. And discharge as well. Another thing to be careful of is just heat, which is caused by internal resistance of the copper and the aluminium and the cells. As long as you deal with heat, then you can charge really at any rate that you can imagine.
So tell me a bit more about the batteries. Let's come and have a closer look at these.
Sure.
So you completely built these battery systems yourself?
Yeah, I designed them all, and we fully manufacture them here in Mitcham. These ones are almost finished. There's going some more balancing technology going in the top here. And we write the software platform that manages them online and lets us manage and monitor every cell. So each one of these modules is series connected. So if you have a look closely at this one's 13.8 volts, 6.2 kilowatt hours, and it's series connected to another one, which is 27 volts, 40 volts and so on, until you get to the end, you're 138 volts across the bus. And these inverters here work from 100 to 170 volts, so it's a good sweet spot in the middle. And from empty to full, these go from about 120 to 150 volts. So it's right in the middle of the inverter's range. And yeah, so if you have a look on here, we have a bit of electronics. It does monitoring and management of the cells. It stores the data for life. So we've got a record of the cell voltages and cell the current coming through the system. And then here we've got a 4G modem that links us off-site. And at the top here we've got 5 power supplies in series that produce 145 volts. So we can charge the system off the grid power to bring the batteries up in case everything went off. Like if you shipped it somewhere and it got stuck in transit and eventually everything went flat, you could recover it just with a generator or a main supply.
So you've actually got multiple redundancies. You've got some solar PV on the roof.
Yeah, there's 5 panels on the roof which come through a charge controller here, which just keeps it alive, so it always can recover using solar power. This is AERL, they're based in Queensland, and this is a little 30 amp regulator that converts 100 and up to 300 volts DC into 138 volts that we can charge the batteries directly from the solar. We can use a generator coming into these inverters that can produce DC and charge the batteries. But one of the problems you know about, that a lot of people know about, is that when you have a flat battery, sometimes an inverter won't actually come on because it needs to see power to come alive, which is why having a DC charge controller is a good idea, because you can always come alive with what we call a black start, where there's only sunshine available. Or alternatively, we can use a small generator through the power supplies to bring the batteries up.
Now, I can see the main switchboard looks pretty impressive on this side of the room. Yeah, tell me what's going on here.
I'll take you through here. So I said before that we had a 50 kVA SWER line coming in. That's this one here, 50 kVA sub incoming line here. So 2 phases come in from the grid in here, then they go out and feed the 2 inputs over here. And then this is the output from those 2 SWER lines after they've gone through the inverter. So we have blackout protection now on these 2 phases that we didn't have before. So they're just spare phases that they can use as single phase feeds around the site. The cable management zone here, where we can bring all the cables in from all the different feeds and manage them from the ground. If you come through the bottom here, we've got 7 cable entry points going out of the container into a big pit, and then they reticulate around the site. So here we've got a main switch, which is our 3-phase main switch, and it's coming from the 3 grid forming inverters over here, and then it's being made available to all of these different buildings around the site. Each one of them has its own Modbus meter, and we scrape the data from the Modbus meter and bring it into a software platform and produce a microgrid report for the client. So the client's got multiple buildings around the site. They don't want someone leaving 3 bar heaters on in the back blocks without them knowing about it, and they want to be able to invoice each building for the use of power. So these are effectively child meters that they can do that with. So each one of these is a different building: mini grid 1, mini grid 2, reception, monastery, sewer, and so on.
Great.
And so then here's the generator input. So there's a 3-phase diesel generator on site already running the sewage system with the water treatment plant, which will be turned off and brought over here as a last mile for the system if there wasn't a grid available.
Now, I imagine there's a fair bit of heat could build up in this room. How do you manage heat?
Yeah, well, we looked at putting an air conditioner in, but we calculated that we probably don't need it given the location it's going to. The batteries are safe up to 60 degrees Celsius, and we've been now testing a module, which I'll show you later on, actually, if you've got time, which has been cycling almost 6,000 times now. We've cycled it, charged it, discharged it, charged it, discharged it every hour for 15, 16 months. And we ran it at 44 degrees Celsius for 12 months to prove that the temperature didn't affect the module. And so far the battery has gone up by 1% in capacity, which is quite unusual for a battery to go up in capacity. But after 6,000 cycles, that simulates about 13 or 14 years of use. So we're confident that the temperature isn't really affecting the modules in a negative way. So therefore we don't probably need an air conditioner. So instead we just put a thermostat controlled fan here, and then a variable speed here. So we can really pull the air out if we have to, or we can have a slower speed for quieter operation. And we're just going to find out what set point, what fan speed works really well on a hot day. And it draws the air through the other door through a filter, and then turns off when it gets to temperature.
Simple. So it's got an active ventilation at the top, yeah, and passive ventilation at the other end of the container, yeah, with filters on the door.
Yeah, and additionally the whole container is built with a thermal break between the outside and the inside. So the way we decided to build the container was we used pallet racking, like a standard commercial commercial racking in a warehouse. And if you have a look just through the gap here, you might see the orange here. So just over here is this orange beams that you'd see normally in a warehouse. And so the frame inside this container is actually a pallet racking frame. And what's good about that is it's very straight and very square and very strong and all very adjustable. So it's kind of like Lego, because every job can be a little bit different. We might need more inverters, more charge controllers, less batteries, it just depends. So having a Lego type system means we don't have to go to engineering all the time. So the whole frame in here is actually built inside the container, and then it's thermally broken from the steel using nylon. So there's no steel connecting the outside to the inside.
So I guess there's two things there. The thermal break means that you're not losing or gaining heat through the body of the shipping container, but also you've got a internal superstructure to attach all your inverters to.
Which is, these things are 115 kilos each, so there's like, 400 kilos to 600 kilos off the wall here. Don't even care, it's extremely strong.
Because I imagine these get shipped around Australia.
Yeah, we shipped one up to Queensland on a train and then a truck, so in train truck to site, and it landed and it was just perfect inside, nothing had moved.
Wow.
This one's going to go by a tilt tray and then a Frenner crane on site. So every job is going to have a different outcome, but really the idea is, can you build a really, really, really long-lasting energy storage container so that the economics are very viable? And so everything in this container here has got a 20+ year design life. So here we're talking about, in SP Pro inverters, 20+ years, no doubt at all in my mind, because they have been running for that for many more years than that since they've been manufactured. These are made locally in Montana. Really high quality product. The guys at Ken and Rod down at Selectronic are great advocates of ours, and we're good supporters of their product. Then we've got the AERL charge controller from Queensland, which is bringing in the solar power. We can have a lot more of those as well. So
I like to say the fun fact about them is they invented the maximum power point tracker, so it's an Australian invention.
They did, yeah. It's like, what else did they invent? Pavlova. Oh, that was New Zealand.
That was New Zealand.
That was a rub up for you, Glenn.
Yeah, and Farlap.
Yeah, Farlap's Australian.
No.
Okay.
Hey, shall we go and check out the outside of the unit so you can show us the panels on the roof?
Yeah, sure.
Okay.
Oh, I haven't shown you the large circuit breakers here yet.
Oh, yeah.
So these are 630 amp, 1000 volt circuit breakers. So they're designed to take an enormous amount of current through them. So there's two strings, and we can remotely trip off one bank of batteries and keep the site alive. So if there's ever a fault anywhere, we detect it, we can turn off one battery bank until it's remedied.
Wow, so you've got remote trip functionality in here.
Yeah, it'll trip itself, but if we wanted to, we could trip it as well remotely.
Yeah.
And we can see why it tripped and what was the cause of it.
Yeah, cool.
Because electronics can fail over time, so we've got to keep an eye on it all. And
that's a big busway you've got there.
Yeah, so this is the cable tray in here where we bring all the cables through from the DC and the AC. We've got large capacity cables coming through here. And then here we've got the combiner where we bring all the DC in. So there's a large pair of fuses in here. We have 2 battery banks on here and then 5 inverters coming off.
So why are there fuses inside the busway?
Well, there's a lot of regulation around fault current and arc flash, and this is our way of dealing with that. So we designed this bus duct system, we called it. We have an optional touch-free connectors on here, which we use on some jobs, and other jobs we plug them and just go directly on with lugs in the back. And the reason that we developed this was to create a safe environment for the worker, and also the regulations tell us we have to keep our current below a certain level. And so we took this bus duct system to the TUV labs in Heidelberg in Victoria, not Heidelberg, Germany, and they did a test on them, and that passed the test of 50,000 amp, 800 volt short circuit.
I think you showed me your little video of that being short-circuited.
Well, that was, so firstly we tested it as it was designed, which was with fuses, and it passed perfectly. We thought, let's just test it by removing the fuses to see what would happen if someone built this without fuses, just as a destructive test, just for fun. And so we took the fuses out and put bus ducts, put copper bars in instead where the fuses were, like putting a nail in your fuse at your switchboard, and then short-circuited it. 50,000 amps, 800 volts, I think 40 megawatts or something, some enormous amount of energy, and it just blew the cables off the wall. But,
wow.
Yeah, good test.
Well, let's go and check the outside of the container.
Sure. So we have 2 doors on the container. And the reason for that is the size of the switch room needs to have 2 doors. You can't just have 1 door on a switch room this big. And they've got a safe exit here, push to exit. Got a nice lamp up there for lighting up the area. And there's the fan there, which I showed you before, which opens up when it's cold, when it gets hot. And up on the roof, you can see we've got 5 solar panels, and they'll just go flat in transit. We couldn't, because it's a 2.9 metre tall container, and there are solar panels on the roof, we go above the allowable height without a permit. And so it was better for us to take the container to site on a tilt tray, which is lower, and that let us keep the solar panels on the roof. We just have to lie them flat for transit.
Right. Yeah, that's cool.
So there's all these logistics questions that come into play around the systems. You've got to be able to ship them, you've got to be able to manufacture them and make them safe and so on. The system's going to be installed on a footing system called Surefoot, which you can look up online. It's a steel plate footing system where you fire steel pins on an angle through into the ground using an electric jackhammer. And there's all different size plates you can buy. And so we've got a kit which has got like a clamping bolt that clamps on the side, and it clamps onto the sides of the container. And so we sent 2 guys up to Bendigo where the system's going, and they put the plates from the ground, set them all out, fired the pins in, and put 4 footing plates in one day. So it's a really effective and efficient way to put a footing system in.
Great.
So they've got footings, container, solar panels, generator, SWER line coming in, and then room to add a solar farm on, and then distribution to lots of buildings around the site. It's all built into a compact container, can be deployed anywhere. The other good thing about doing this, instead of paying the grid for a grid upgrade, is you have an asset here. And this thing's designed to last 30 years. Like, all the parts in it have got a really long design life. So you're buying an asset that you're going to be able to relocate if you have to. So if you're a mining site, for example, and your mine's got a 10-year life, and you went to the grid and you said, I want to get a grid upgrade here, they'll charge you the $500,000 or $1 million for the grid upgrade. And then when you leave, they'll go, thanks very much. Whereas if you buy $500,000 or $1 million energy storage system, depending on how big it goes, obviously, then you've got an asset that you can move to your next site and you don't have to pay the next time. And that's been really attractive for a large mining client we've got in Western Australia, where that was their exact question, was how long will this last and can we relocate it? And the big answer was yes, and I said that sounds like just what we want. So,
great. Thanks very much, Paul.
No worries. Thanks, Glenn.